This video gives some basic examples, definitions, and notation for permutations and combinations. How many ways are there to pick a president, vice president, and treasurer for a club if the club has 20 members? Well, there are 20 options for how to pick the president. And for each of these options, there are 19 people left that we could pick for vice president. This is assuming that you can't be both president and vice president at the same time. These have to be two different people. Once we've picked our president and vice president, there are only 18 people left that we can choose for our treasurer. Therefore, the total number of ways is 20 times 19 times 18. This works out to 6,840 possibilities, though I'm more interested in how we got the number than what the actual number is. Suppose instead we need to pick a team of 3 people from a club of 20 people. This problem is different from the last problem because the people on the team don't have any assigned roles. And therefore, if we pick, say, Annie, Bert, and Catherine, that's the same as picking Bert, Annie, and Catherine. Whereas in the first problem, those were different choices since Annie being president is different from Bert being president. One way to count the possible teams is to do the same thing we did before, count them where order matters, but then divide by the overcount. Since there are 6 possible ways of arranging 3 items, but we want all those 6 ways to count as the same team, we could use the previous problem, find the ways of picking 3 people where order matters, and then divide by the overcount. This gives us the total number of possible teams, which works out to 1,140, a smaller number. Let me pause for a minute to talk about where this number 6 comes from. 6 is the number of ways of arranging 3 things in any possible order. But instead of writing them all out, I could have thought more abstractly. The number of ways of arranging 3 things is 3 times 2 times 1, or 3 factorial, because we have 3 choices of what to put in the first spot. And then once we've chosen that, we have 2 possible choices left for what to put in the next spot. Once we've chosen the first 2, we only have 1 choice left for the last spot. So if we modify the problem a little bit and have to make a team of, say, 7 people from 20 in the club, how would the answer change? Well, we would need to pick first 7 people in order. So that'd be 20 times 19 times 18 times 17 times 16 times 15. That's 6. I need to pick 1 more. But that counts the number of ways where the order matters. The order we pick them doesn't matter. So I have to divide by the number of ways of ordering those 7 things. I would divide by 7 factorial. The first example is an example of a permutation. A permutation is a way of counting things where order matters. The second example is an example of a combination. A combination is a way of counting things, like people on a team, where order doesn't matter. Next, let's look at some general formulas for permutations and combinations. For positive integers n and r, where r is between 0 and n, the number of ways of arranging n different objects in a row is given by n factorial, n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. This makes sense because we have n choices for who to put in the first place. Once we've picked that person, we have only n minus 1 choices for who to put next, and so on. But if we're not arranging all n objects, just r of them, then we're finished making choices after only r steps. For example, in the president, vice president, treasurer example with the 20 club members, we had 20 choices for the first person, the person who's going to be president, 19 choices for the next spot, the vice president, and 18 choices for the third spot, the treasurer, and then we stopped choosing. So we stopped after r equals 3 numbers, and notice that this number 18 is equal to the top number 20 minus 3 plus 1. More generally, when we have n objects and we're just arranging r of them in a row, we have n choices for the first object, n minus 1 choices for what to put next, and so on. but we stop after our factors at the number n minus r plus 1. Those are all permutations because order matters. If instead order doesn't matter, then that's a combination. The number of ways to choose r objects out of a collection of n objects is given by this formula because first we're arranging the r objects in order, like we did in the previous permutation, but then we're dividing by the number of ways of ordering those r objects because the order actually doesn't matter. If we didn't divide, we'd be overcounting because we'd be counting each set r factorial ways, once for each way of arranging it. This matches up with our problem involving the team of 3 players out of 20 club members, which we found by doing 20 times 19 times 18 over 3 factorial. Sometimes this formula for combinations is written in a more concise notation here. Let's unpack why that works. If I have n factorial over r factorial n minus r factorial, I can write that as n times n minus 1 times n minus 2 all the way down to n minus r plus 1, and then the next one would just be n minus r, and then n minus r minus 1 all the way down to 3 times 2 times 1. Now I'm going to divide that by r factorial times n minus r factorial, but notice that this part right here is just another way of saying n minus r factorial, since I'm starting at n minus r and going down and down until I get to 1. Therefore, I can cancel this part with this part and get my original expression, my original formula for combinations. So these two formulas are indeed the same thing. There's also other notation for combinations and permutations. Sometimes permutations are written P of nr and combinations in the similar formula C of nr. And frequently combinations are written in this big parenthesis notation called choose notation. This is read n choose r, which makes sense because it's a number of ways of choosing r objects out of n. There are other notations for permutations and combinations, but I won't give them all here. Let's apply these formulas to a couple of examples. Suppose you have 7 swimsuits, I know that's a lot, and you want to pack 4 of them, I know that's also a lot, for your spring break trip to the beach. How many ways would there be to do this? Well, the order that you pack the swimsuits shouldn't matter, you're just throwing them into your suitcase. So this is going to be a combination problem. I'm choosing 4 swimsuits out of 7, and so that's going to be given by 7 factorial over 4 factorial times 3 factorial. I get the 3 as 7 minus 4. Notice that 4 and 3 add up to 7. That's a way to check that I'm doing the right thing here. I can write this out and cancel. In fact, I could have just left out these pieces to begin with and used the other formula for combinations. If I cancel some more things, I get 35 ways, which is not really such an overwhelming number for somebody who has 7 swimsuits. One thing you might notice about this problem is that the formula for 7 choose 4 is actually the same as the formula for 7 choose 3. This makes sense because choosing which 4 to pack is the same thing as choosing which 3 to leave at home. In this next problem, you have 3 nieces, Annie, Bella, and Cameron, who all like to go to basketball games. And you have a ticket to each of 10 home games. How many ways could you give each niece a ticket to one game? So what I mean by that is one niece gets a ticket to one game, the next niece gets a ticket to another game, and the third niece gets a ticket to some third game. If we just wanted to pick 3 games out of 10 to give tickets for, that would be a combination. But that's probably not the right answer to this problem because giving like Annie a ticket to the UNC Duke game is going to, and Bella a ticket to like UNC somewhere else, UNC State, that's going to feel differently to Annie and Bella than if we swap them, right? So it matters which game is being assigned to A and which game is being assigned to B, and which game is being assigned to C, of course. Since the order does matter, this is a permutation. There are 10 possible tickets I could give to A, and once I've decided what to give to A, there's 9 tickets left for B and 8 tickets left for C. So the number of ways of doing this would be 10 times 9 times 8, which is 720 ways. Here we have a permutation, and here we have a combination. This video gave some basic examples of permutations where order matters and combinations where order doesn't matter.